Hi guys, today we are going to do the Chinese remainder theorem. Let's start by seeing what is Chinese remainder theorem and when can we apply this. So Chinese remainder theorem is used for solving a system of linear congruences where the moduli are pairwise relatively prime. It all started in the 1st century AD. A Chinese mathematician posed a problem. He asked, what number yields the remainders 2, 3 and 2 when divided by 3, 5 and 7 respectively? Using the notation of congruence, if we write the model of this problem, we will get a system of linear congruence. X is congruent to 2 mod 3, X is congruent to 3 mod 5 and X is congruent to 2 mod 7. Because here we can see it says let the number be X and when we divide by 3, so we take a 3 in the modulus, we get the remainder 2. When we divide by the integer 5, we get the remainder 3. So when we divide by 5, we get the remainder 3. And when we divide by 7, so we take modulus 7, we get the remainder as 2. So the whole thing has been put in congruence and we get a system of congruence. We can see all these congruents are linear. There is no power to x. Another thing, the modulus 3 and 5, we can see pairwise, they are all relatively prime. 3 and 5 have a GCD1, 5 and 7 have a GCD1, and 7 and 3 also have a GCD1. So how do we solve such a problem? What we do is, first we will find the initial solution to each congruence. We see that 2, 3 and 2, they satisfy all the three congruents. We'll go back and see. Here 2 satisfies this, so C1 we take as 2. 3 satisfies this, so we take the initial solution C2 to be 3. And 2 satisfies the last congruence, so we take 2 as our C3. These were our C1, C2, C3. Then we know that each congruence starts with X is congruent to your value. X is congruent to 2. We don't have a coefficient here. So our A1 is 1, A2 is 1 and A3 is 1. Come to our modulus. Now, first one has a modulus 3. Second congruence has a modulus 5. We call it M2. M3 is 7, which is the modulus of the third congruence. We've already seen all of them are pairwise relatively prime. Capital M is nothing but the product of all the three modulus and it gives us 3 into 5 into 7, which is 105. Let's define N1, N2, N3. What are N1, N2, N3? They are found by dividing the capital M by each Mi. So if we divide 105 by 3, we will get 35. When we divide 105 by 5, we'll get 21. And when we divide 105 by 7, we get 15. Now we'll find the inverse of each of these Ni, N1, N2 and N3. And we can see N1 bar, N2 bar and N3 bar, which we call as inverses. They are found to be 2, 1, 1. We can check that. What is an inverse? Inverse N1 bar is nothing. When it is multiplied to N1, it should be congruent to 1 modulus of 3. We see that 2 satisfies this congruence. N2 into N2 bar should be congruent to 1 mod of 5 and N3 bar should be congruent to 1 mod of 7. So now what is the solution? Whatever we needed, we have found. What we do, we'll multiply C1 N1 N1 bar plus C2 N2 N2 bar plus C3 N3 N3 bar. And this is what we get. 2 into 35 into 2 plus 3 into 21 into 1 plus 2 into 15 into 1. Now this gives us 233, and this would be modulus capital M. For us, capital M is the product of all the three moduli, 3, 5 and 7. So this gives us, this is 233 mod of 105, which is congruent to 23 mod of 105. We can see that 23, if substituted, satisfies all the three congruents. So we will get a general solution, 23 plus 105t. We'll write x is equal to 23 plus 105t. Now, let's see, there's another method of solving such a system of congruence. Let's take the congruence with the highest modulus. We know the last congruence was x is congruent to 2 mod of 7. We can see 2 is one of the solution, 2 satisfies it, and the general solution will be x is equal to 2 plus 7t. Now, if I take t as minus 2, we will get x is equal to minus 12, and this will satisfy the second congruence, x is congruent to 3 mod of 5. If you put minus 12 in this congruence, we see minus 12, and we bring the 3 on the other side, minus 15 will be divisible by 5. So, minus 12 now satisfies two congruents, x is congruent to 2 mod 7 and x is congruent to 3 mod 5. Which means, if we combine these two, a common solution to these two congruents will also be a solution to the product of their moduli, 7 into 5, which is 35. This 7 into 35. So minus 12 is a solution to my x is congruent to minus 12 mod of 7 into 5, 35. This will give us the general solution, x is minus 12 plus 35. Let's take some variable t star. For t star is equal to 1, we get x is equal to 23. And if you put this 23 in the third congruence, x is congruent to 2 mod 3, it satisfies. Hence, the final solution is x is congruent to 23 mod of product of all the three moduli, which is 105. Chinese remainder theorem can also be used for linear congruence with modulus which can be factorized into product of primes. Let's look at an example. If we are given solve 2x is congruent to 13 mod of 69, we can reduce the congruence to a system of congruence. As 69 is 3 into 23, we get 2x is congruent to 13 mod 3 and 2x is congruent to 13 mod 23. We have written this single congruence as a system of two congruents. And for this, when we use the Chinese remainder theorem, we see that our A1 is 2. This is our A1. A2 is 2. C1 minus 1 satisfies this equation, this congruence, sorry. So C1 is minus 1. 18 satisfies the second congruence, so C2 is 18. N1 is 23 and N2 is 3. And the bars, N1 bar is 2 and N2 bar is 8. This will give us the solution as 386 when we substitute the values mod of 69. Or it is congruent to 41 mod of 61. Thank you for watching.